Models of interval timing. The system that underlies interval timing is typically assumed to be different than the system that allows for circadian timing. That said, different models of interval timing exist, three types of which do well to describe the current data and will be described here. Although there is no consensus regarding which model is best, each has inspired new research and paradigms. Ultimately, it may be that advances in the neuroscience of timing will help to decide among these models, a topic that will be considered in Box 6.1. Box 6.1, Interval Timing in the Brain. In humans, the neuronal bases of interval timing have been hypothesized to comprise a broad system spanning the thalamus and striatum, as well as the frontal and parietal cortices. The details of the system, including the individual functions of different brain areas, have yet to be determined. One goal of the ongoing research is to utilize neuroscience findings to elucidate the cognitive processes of timing by distinguishing among the models presented above, but along the way, the research has also improved our knowledge of some neurological disorders. Early work found initial support for the information processing model from pharmacological manipulation involving dopaminergic drugs. Data consistent with a separate clock component came from studies with rats in which methamphetamine, a dopamine agonist, led to peak responses that were shifted to the left of peaks in control conditions. That is, the increase in dopamine seemed to act in such a way as to speed up a clock. In contrast, haloperidol, a dopamine antagonist, caused a rightward shift of deceleration of the clock. However, subsequent data have been inconsistent, with some studies showing mixed results or suggesting that the clock was actually slowed with dopamine increase. A direct relationship between dopamine and an interval timing clock has also been challenged by studies of neurological disorders. Patients with Parkinson's disease, in which nigrostriatal dopaminergic projections degenerate, show worse interval discrimination when they are not taking dopaminergic medication, L-DOPA, than when they are taking the drug. This finding may appear to be in support of the pharmacological studies just described, but actually, for these patients, timing did not generally appear to slow down, as would be predicted with a decrease in dopamine. Instead, two comparison times were judged more similarly, as if one interval was sped up and the other one slowed down. Currently, none of the existing cognitive models has complete support from neuroscientific studies, though as research begins to define the roles of the various areas within the timing network, thalamus, striatum, frontal and parietal cortices, certain models may gain support. In turn, the cognitive effects of neurological disorders may be better understood. Additionally, as knowledge is gained regarding how humans and animals process other magnitudes, such as number, the understanding of timing processes in the brain may become clearer. The information processing model of timing, also known as the scalar expectancy theory or the pacemaker accumulator model, the information processing model by Gibbon, Church, and Meck, 1984, is possibly the most well-known of the three theories. In general, it is a model of the manner in which a current event may be compared to a representation, stored in memory, of a past event, figure 6.4. More specifically, the model is based on a hypothetical pacemaker that emits pulses at a constant rate. When a to-be-timed event starts, a switch is activated, allowing pulses to be accumulated until the event ends. At the end of the event, the switch is deactivated, and the information in this accumulator is held briefly in working memory. The contents of working memory are transferred to reference memory, which also contains information as to whether a response, e.g., lever press, was rewarded. For subsequent events, e.g., trials in an experiment, the value in working memory will be compared to the contents of reference memory, and a decision will be made to respond or not to respond. Figure 6.4, the information processing model of timing from Gibbon et al., 1984. At the start of an event, a switch is closed, allowing signals from a pacemaker to accumulate. Working memory of the magnitude can then be compared to reference memory to guide a decision process. Okay, so it's a flowchart that starts with signal, and the pacemaker also leads to switch. So they both lead to switch, and the switch leads to the accumulator, which is the clock process, which leads to working memory. Working memory splits and leads to reference memory, a memory process, and working memory also leads to the comparator. And now working memory and reference memory both lead to the comparator, and the comparator leads to a yes or no response, which is the decision process. The comparison process works by computing a ratio of the value in working memory to the rewarded value that is stored in reference memory. It is commonly assumed that when reference memory is accessed during the comparison phase, a single criterion value is obtained. Yet, it is proposed that for each decision, trial, this value can come from a distribution of different criterion times stored in reference memory. This variation among criterion times is the result of variability in the speed of the pacemaker between trials, and if the pacemaker varies, more error will naturally accrue for longer intervals than shorter ones. Thus, by incorporating a source of variance, the information processing model accounts for the fact that timing is scalar in that the variance increases with the length of the timing interval. The oscillator model of timing. The information processing model has proven seminal in the study of interval timing, but it may not fit the actual neurobiology of timing organisms. One model that can potentially be a better fit to the manner in which the brain works is the oscillator model. Although the details of the model go beyond the scope of this book, several aspects of this connectionist model can be explained by building on the information processing model. First, using a suggestion by Gillistel, 1990, this model replaces the pacemaker with multiple oscillators. That is, this model no longer posits a pacemaker that emits pulses, but instead considers the presence of oscillators, mechanisms that fluctuate in a rhythmic, sinusoidal manner. Importantly, each of these oscillators is proposed to have a different period. For a timed event, the duration is coded not by an accumulation of pulses, but by vectors that represent the phase of each of the oscillators. Further, for this model, the reference memory is stored differently than it was in the information processing model. In the oscillator model, memory for intervals is stored within a matrix, familiar to those with a background in linear algebra, rather than as a distribution of values with a mean close to the actual interval. Though mathematically complex, the oscillator model has the advantage of potentially being a more accurate fit to the underlying biology. Since single neurons and groups of neurons can generate oscillatory activity, the model might better guide the neuroscientific study of timing. However, in its present form, it is meant to be a cognitive model, presenting only analogs to brain structures. Additionally, there are limitations to the model, including assumptions that must be made to fit Weber's law that still require verification. Models explaining timing without internal clocks. Some explanation of interval timing do not incorporate a pacemaker, oscillators, or other clock-like mechanisms, and instead account for timing in other ways. The behavioral theory, for example, describes timing in a more traditional behavioristic manner, rather than through a cognitive model like those described above. Because animals often engage in relatively stereotyped behavior, starting at the beginning of a to-be-timed event, the behavioral state at the time of reinforcement can come to be associated with the reward. An experiment by Machado and Keene, 1999, illustrates this process. Pigeons observed a light turn on for 4 or 16 seconds, and depending on the duration, pecking a blue or red key would be rewarded. After some experience with these contingencies, the light started to elicit a series of responses, starting with pecking the light and then moving around the box. On most 4-second trials, the birds were still pecking at the light when it turned off, and at this point, they went to the corresponding key. On the 16-second trials, they had begun to move around by the time the light turned off and then went to the appropriate key. It is thus possible that the correct responses were not due to an internal timing system, but instead may have been the outcome of the formation of associations between certain behaviors and a key that yielded reward. Another explanation for how animals may come to respond after short intervals without a specialized internal clock comes from a memory model by John Staden and colleagues, Staden 2005. In laboratory situations in which animals receive food at regular intervals, it is possible that the decay of memory from one reward to the next can itself be associated with food. If, say, a pigeon receives reward for pecking every 30 seconds, any one event of reward will create a memory trace. This memory will become weaker over time, and its strength at 30 seconds may come to be associated with the reappearance of food if the rate of decay is similar trial after trial. Conclusions. Despite clever, well-controlled research and models such as these, it has been difficult to define the process of interval timing. Models must fit the behavioral data, but also should find some analogy with neurobiological data, the latter of which is relatively new and improving as technologies advance. Modifications of old models or creation of new models will likely be necessary. It might also be the case that the processes outlined in the models presented above are not mutually exclusive. For example, an interval timing system may serve to encode durations of signals, but then certain behaviors could become associated with post-interval responses. Additionally, as the next sections will detail, similarities with the process of counting may ultimately improve our understanding of timing. The approximate number system. Discriminating between two durations and discriminating between two arrays of objects share a common feature. Both are instances of discriminating magnitude. Indeed, many have hypothesized that timing and numerical processing originate from a similar, if not common, representational system. One piece of evidence for this hypothesis is that numerosity discrimination also fits Weber's law. Other evidence comes from studies showing that animals keep track of number and time simultaneously. In 1983, for example, Meck and Church presented rats with either 2 or 8 bursts of noise that were 1 second each. Reward could be obtained if the rats pressed one lever if 2 bursts had occurred, and another lever if 8 bursts occurred. In this situation, number and time co-vary. 2 bursts took 2 seconds, and 8 bursts took 8, figure 6.5. After experience, trials were presented that tested either for control by time or control by number. On trials testing number, either 2 or 8 bursts were played, but each occurred over 4 seconds. On trials testing timing, 4 bursts were played either over 2 or 8 seconds. The rats remained accurate regardless of which dimension they were tested on. They responded with the long lever either for 8 seconds or 8 bursts, and the short lever for 2 seconds or 2 bursts. Figure 6.5. Example training and testing stimuli from Meck and Church, 1983. Each hill represents a stimulus, sound burst, and its duration. Okay, so they're just showing the experimental conditions that the rats were trained on and tested on, like how many sounds per how large of an interval. Similar results were found for pigeons, suggesting that across animals, the duration and numerosity features of stimuli are processed simultaneously. This hypothesis will be revisited throughout this section, though the primary focus will be on how animals and humans represent number. Then, in section 6.4, a second proposal will be explored, one that considers a separate system for representing small numbers. Importantly, though, this chapter will follow the recent traditions of this field of study by limiting the term counting to situations in which quantities are precisely labeled with a symbol system, e.g., Arabic numerals. In fact, it is likely that the numerical processing that is detailed here forms the foundation for the mathematical counting skills that humans learn. See Box 6.2. Box 6.2, the approximate number system and math skills. Although it would appear that infants and animals share a similar approximate number system, humans in most cultures go on to learn a representational system for formal mathematics and counting. Whereas the approximate number system is imprecise and comparisons between numerosities are dependent on ratio differences, the language-based representations of number are exact. With the former, one can quickly determine that an array of 16 is different than an array of 32, but with the latter, one can know that there is exactly a 16-unit difference between these arrays, and that 16 indeed also differs from 17. Humans use the approximate number system throughout adulthood, and the speed at which adults determine which of two quantities is greater continues to depend on the ratio difference. Several researchers have proposed that this approximate number system forms the foundation for formal mathematical computation and counting, and research has begun to support this claim. In a study with 3 and 5-year-old children, using a task similar to the relative numerosity experiments by Honig and Stewart, 1989, described above, performance correlated with scores on a standardized mathematics test even after children's age and verbal skills were controlled. Similarly, at 14 years, variation in children's performance on an approximate number task correlated with variation in mathematical ability after controlling for more general cognitive abilities. In adulthood, the correlation continues to hold. As strong as these findings are, there are also studies that suggest that more research is needed. The relationship is not always found in studies with children, or if found, a similar relationship is not always found for adults. At the very least, it may be that the measurements used matter. Some mathematical abilities may be more related to the approximate number system than others. Given the correlational nature of the research, it is logical to ask whether there is truly a causal relationship such that enhanced approximate number ability makes some people better at math. Although this area of study is still new, Fegenson and colleagues, 2013, have proposed a causal relationship based on 3 sets of findings. Individual differences in the approximate number system exist even in infancy. The precision of this system predicts math scores later in development, and training the approximate number system may improve formal math ability. There is still much to be examined, of course, but the comparative study of numerical competence may ultimately play a role in our understanding of formal math and perhaps advanced mathematics education. Discriminating the number of responses. When human adults are told to press a key a certain number of times as fast as possible, they can be reasonably accurate, even if counting is made unlikely by asking the participants to say the word "the" with every key press. That is, humans have a sense of how many times they have responded, even without engaging the verbal counting system. Rats appear to be able to keep track of responses as well. In one study, each rat had to press a lever a certain number of times, ranging from 4 to 24 across different groups, and then place its head into a food tray to receive a reward. If a rat moved to the food tray before having completed enough presses, the trial was ended and a new one began. The peak response at the food tray occurred at or near the correct number of presses. For both the humans and rats, though, there was variability. Key or lever presses were not always exact. Similar to the studies of timing, the variance increased as the number increased, following Weber's law. Thus, not only do tasks requiring subjects to keep track of the number of responses show some of the same variability signatures as timing, these signatures are present in both rats and humans. That is, although humans have an ability to learn symbols for numbers and engage in counting, they also have a system for non-verbally estimating numerical value that is shared across species. Comparing numerosities. It is relatively easy to look at the third array in figure 6.6 and quickly determine that there are more O signs than X signs. It is not immediately apparent that the ratio is 70-30, but there is clearly a difference in relative numerosity. The ability to gauge which of two arrays has more or less has obvious practical advantages. It could, for example, be a cue to ideal feeding locations. Outside of the visual domain, recognizing the number of individuals in a rival group by using their vocalizations relative to the size of one's own group might impact decisions regarding aggressive responding. Figure 6.6, Example Training and Testing Stimuli from Honig and Stewart, 1989. In this example, the test array has a greater number of the previously rewarded O's than the X's, and the rate of pecking responses was directly related to the proportion depicted in the array. Okay, so in training, it's all O's, and a peck equals a reward, and there's also an array in which they're all X's and a peck equals no reward. Okay, so you want to peck the O's and not peck the X's in training, and then in testing, you can see it's a variety of X's and O's, but you can see that there's more O's. And it says the rate of pecking responses was directly related to the proportion of the testing array, so like it was 70-30 O's to X's, so they pecked about a 70% ratio. In a classic example of relative numerosity discrimination, Honig and Stewart, 1989, began by training pigeons that pecking at an array of all red dots would yield a reward, but responding to an array of all blue dots would not yield a reward. Once pigeons were responding, accordingly, the test trials were included that had red and blue dots intermixed, analogous to the O and X signs in figure 6.6. On these test trials, pigeons' rate of responding was directly related to the proportion of red dots. That is, pigeons pecked more frequently if there were more red dots than blue dots, and the responding increased as the number of red dots increased. The results could mean that pigeons are sensitive to relative numerosity, but an alternative explanation exists. In these arrays of dots, number is confounded with surface area. An array of all red dots may have, say, 36 dots, but it also has a certain surface area of redness. An array of 20 red dots to 16 blue dots will have more red color than blue color. Thus, correct responding in Honig and Stewart's experiment may not have been due to comparing numerosities, but by comparing surface areas. In the natural world, these two qualities often co-vary, yet if it is the ability to enumerate that is the focus of a research question, then an experimental design would have to differentiate between them. Follow-up studies to Honig and Stewart, 1989, did just this by controlling for surface area in various ways, e.g. altering the size of the dots, using X's and O's instead of dots, etc., and pigeons still showed the same pattern of results, providing evidence that they were indeed comparing numerosities.